All right. I will begin with a word of prayer. Dear Father, we thank you again for this opportunity we have just to meet together and study your creation. I just pray that you be with us today. Help us to, again, Lord, glorify you in what we do. I just pray you continue to encourage these students as they work on this course and others this semester, just each day, Lord, to do their best for your glory. In your name I pray, Lord Jesus. Amen. Oh, yeah, let me get rid of this offensive group theory. And trivial number theoretic comments. Oh, be gone with you. All right, guys, so let's do number one here. So cosine of pi j is equal to minus 1 to the j, right? Because if you look at it, cosine of pi is minus 1, right? Cosine of 2 pi is 1. Cosine of 3 pi minus 1, right? Right? So if you look at it, then the sum of cosine pi j over j squared, this is just equal to the same as the series minus 1 to the j over j squared. So if you write that out, what is that? You've got minus 1 plus 1/4 minus 1/9 plus 1/16, right? You can identify a sub j equals to 1 over j squared. Then if you do that, this is what? This is like minus a sub 1 plus a sub 2 minus a sub 3 and so forth, right? Which shows that it's alternating. All right? So yes, it's an alternating series. Does it converge? Well, this right here is positive. And you notice that dAj, I mean, I don't know if, I'm not sure I need to do this, but dAj, dj, extending j continuously, is minus 2 over j cubed, right, which is less than 0. So therefore, a sub j equal to 1 over j squared is decreasing, right? So here, extending j continuously. Since, of course, we can't differentiate with respect to j, technically speaking. So if you like, I'm thinking f of x equals to 1 over x squared. Differentiate it, you get minus 2 over x cubed. That's a decreasing function, so it matches the sequence, discrete values, x equal to whole numbers, and so. But I don't want to write all that, so I just say this, and okay. All right, so it's decreasing, it's positive. What's the limit? This goes to 0 as j goes to infinity, right? So therefore, by the alternating series test, S converges. Okay. Does that make any questions about that? Yep.
Didn't you just say it's the alternating equals 2 series?
Yeah, that would have been. I mean. Well, yeah, but I don't have an alternating P series theorem that I've proved. So, if you want to prove at the start of your test that any alternating P series converges if P is greater than or equal to 1, you're welcome to do that. Wait a minute. It's better than that, isn't it? Oh, oh, you used absolute convergence. Yeah, that's cool. So you're like, take this series, form a corresponding series of the absolute value of the terms. That's P equals 2 series. It converges. Therefore, the original series converges by the absolute convergence implies convergence theorem. Sure. That's great. How about 2? Here, if you look at it, notice that e to the n over n squared, right? What's the limit as n goes to infinity of e to the n over n squared? Infinity. Well, I would say that that's infinity over infinity, so I'm going to use L'Hopital's rule. So that's the limit e to the n over 2n, right? And then L'Hopital's rule again. Obviously, I've extended n to be I've extended n continuously, right? Right, and yeah, so that equals infinity, which implies that the limit as n goes to infinity of minus 1 to the n over e to the n over n squared does what? Right, does not exist, right? It definitely, in particular, we can definitely say this, more to the point, this is not equal to 0, right? So therefore, this series diverges by what? In this case, the nth term test. You guys have grown accustomed to the kth term test. This is the nth term test. There's also a jth term test and a Pac-Man term test, and there, I mean, whatever. You get the idea. I hope. Any questions? Yeah.
What if I used log at the beginning of that, log of the top log of log, then you use log?
Log.
Then you get rid of the e.
Well, how would you use log? Log on what? Log on this?
Yeah, the log on the top and bottom.
I mean, I can't take the log of that, right?
No. Log on that.
This one, but why would you take the log of that?
You get rid of the e, and then you're left with n over L.
I mean, if you're saying that you use that the limit as n goes to infinity of like e to the n over n squared, right, is equal to you know, the exponential of the limit as n goes to infinity of of log, natural log of e to the n over n squared. I mean, I'd be okay with that, but I wouldn't. I mean, I wouldn't do it, but I don't need to do it. I mean, you're just taking the log of the limit. I mean, what are you doing?
Never mind.
Oh, okay. I mean, it's fine. I do, you know, these kinds of questions are good. More questions you guys ask, the better, really. Within reason. I mean, they have to be math questions. I don't really, if you start asking me questions about NASCAR, I don't really have anything to say, you know. Sorry. It's just not part of my culture. Let's see here. Ew. Okay, so something I should point out and talk about here for a couple minutes is this theorem. I mentioned it last time, but let me talk about it again. If you have an alternating series, right? And here the starting point matters a little bit for the argument, but not for the result. K equals 0 to infinity, minus 1 to the k, a sub k, if this is equal to L, right? Now that would happen if what? You know, we're assuming that a sub k are positive, that a sub k plus 1 is less than a sub k, right? Decreasing, strictly decreasing, really. And what else? A sub k goes to 0 as k goes to infinity. So given those conditions, it's a convergent alternating series, right, by the alternating series test. And then here's the deal. The nth partial sum, all right, minus L is going to be less than a sub n plus 1. So let's see here. Well, I don't know. The time to prove that was yesterday because we had everything in front of us in terms of the partial sums and all that. Let's see here. How can I argue it? The proof basically is this. Last time we did what? We showed that S2m was what? a decreasing sequence, right? And if you think about it in this current context, it's a decreasing sequence which converges to what? It converges to L, right? And so what does that tell you? On the other hand, S2m plus 1 is what? I mean, this is equal to S2m what? Minus what? Minus a sub 2m plus 1, right? So he points out that if you look at it then, S sub n minus L, all right, is less than the absolute value of Sn minus Sn plus 1. Now, is that obvious to you guys? I'm not sure. Before we complete this proof, let me stop and do an example for you so this makes more sense to you. Let's look at the alternating harmonic series again. N equals 1 to infinity, minus 1 to the n plus 1 over n. Right, so this is 1 minus 1/2 plus 1/3 minus 1/4 and so forth, right? So we can draw this giant number line here. Here's 1. Here's 0. Here's 1/2. All right, so let's see here. So S1 is this, right? What's S2? S2 is the first two things. It's 1 minus 1/2, right? Which is 1/2. So right here is S2. Where's S3? Right, S3 equals 5/6, so that's over here. And what about decreasing sequence? I'm not sure I believe that. I think I copied something down wrong. How about S4? S4 should be 5/6 minus 1/4, right? Which would be what, like 20 minus 6, 14/20ths? AKA 0.7, right? So that's like here somewhere. How about S5? S5, I do what? I add a fifth, right? So, wait a minute. Sorry, I got lost in the numbers here all of a sudden. 0.5 is fine. 0.5 plus a third is 0.833. What's that? Well, yeah. I agree with that. Where's S5 though? S5 is plus 1/5. Plus, that doesn't... Point... What? Oh no. Oh no. I'm confused. Like, see, the thing is, the theorem is that the difference between Sn and L is smaller than an plus 1, right? Oh. I'm sorry. It's bothering me. I thought that they had to get closer, but they're getting closer to each other, but you know, S5 is what? S5 is, yeah, it's 0.9 unless I'm making a mistake. Oh, thank you. That is very, very important. That's the mistake right there. Okay, thank you. What's 14 over 24 equal to? 7 over 12, which is what? 0.583. Okay, thank you. That 20 was what was blowing my mind. Okay, thank you. We fixed it. 0.58. So it's more like over here, right? And then S5 is like here. So S5 is equal to 0.783, right? And then S6, we subtract what? 1/6, which is what, like 0.166. So it's like 0.17-ish. So it's where, like 0.61? I mean, S6 is here, right? So you can see that they are, so let's see here. The odd terms, what? We have S sub 2m plus 1 going to L. These are decreasing, right? And over here, well, yeah. Over here we have S sub 2m going to L, and S is increasing, right? Why is it not legitimate to compare the increasing and decreasing here and there? Why are these different?
Because that one's strictly decreasing?
No. Starting point. This starts at 0. This one starts at 1. So the pluses and minuses are different. Like the pluses go to, on this one, right, if I write it out, the pluses are on, so the pluses are on the even terms here, right? That's why the even partial sums are decreasing. Over here, the pluses are where? In the odd terms, that's why those are decreasing. And conversely, the minuses are aligned with the even terms, and that's why they're increasing. But I'm an idiot. Anyway, yes.
Is that what you meant by rearranging the terms?
Oh, we haven't rearranged terms here yet. I don't plan to do that.
You just mentioned something about it yesterday.
Yeah, that's another thing. Sorry. Anyway, from the proof that we went through yesterday, you could see that this was decreasing, and I think, well, anyway, the point is, if you look at the difference between subsequent partial sums, it's going to be less. Well, this actually is what? This is equal to a sub n plus 1, right? Anyway, that's the theorem, is that if we take the difference between the nth approximation to an alternating series and the actual result of the series, the thing to which it converges, that's smaller than the next term we didn't use. So, sorry if I've muddled the proof of it. Well, we defined the a sub n to be positive, so I don't need absolute value there. If you'd like to add absolute value to it, you're welcome to. Here, let me show you a precise example here. This example 5 from your text, it's pretty nice. Pretty powerful example. We're supposed to give a numerical estimate for this series. We're looking at the sum, k equals 0 to infinity of minus 1 to the k divided by 2k plus 1 factorial. All right. And so let's see, that's equal to what? That's equal to 1 minus 1 over 3 factorial, right? Plus 1 over 5 factorial minus 1 over 7 factorial plus da da da. And he wants us to give a numerical estimate for this series correct to, he asks for 3 decimal places. All right. Okay, so we're going to basically use this. Now, if you think about 3 decimal places, what's a good error for that to be? This thing right here is the error in the nth approximation. You call it epsilon sub n or something if you wanted to. So we want epsilon sub n, which is the absolute value of the real thing, which we don't know, minus the nth partial sum. We want that to be at most what? If we want 3 decimal places, you're thinking about, 0 point, the first thing, the second thing, the third thing. You want to know those. And so to make sure this doesn't change the outcome, you can make that what? I mean, you got choices. I would just make it, if you want to be really greedy, I guess you could put a 4 here, right? That wouldn't change the outcome, right? But as a rule, I would just set this equal to 0.000, let's see here, best case scenario, I suppose 4. I usually put 1 just to be generous. There's some wiggle room here depending on what your convention is. I'm not a numerical analyst. I don't have a real, I could see the reason. I mean, some people put a 5 here. Seems a little dicey, but you could logically put a 5 there probably. Okay, we want the error to be at most that. Let's just choose it to be that, okay? That actually makes the fourth decimal place somewhat reliable, right? That makes the 4th decimal place reliable up to like 1 digit up or down, right? Maybe that's 2. Should I put a 5 there? What do you guys think? What's your feeling about this? Correct 3 decimal places. What would you like that to mean? Let's make an agreement, right? We're trying to decide truth. Truth is decided by consensus. This is your opportunity to participate. I'm being slightly facetious. But this is, I think we probably should put a 5 there. I think that's what your book does, right? That worries me slightly, though, because if it actually was equal to 5, strictly equal to 5, then what? You could have a roundup, right? But I think that won't actually be strictly equal to 5 because we have a strict inequality here, right? So if I make this equal to 0.0005, that actually isn't going to result in a real error of 0.005. So that danger is not realized. Okay, so what do you want? You want this to be less than a sub n plus 1, right? in order for S sub n to make the error smaller than 0.0005. So we just calculate them, right? I'll start you out. A sub 0 is 1. Okay. A sub 1 is what? 1/6, right? Yeah. A sub 2 is 1 over 120. So this is, roughly speaking, 1.116 or 17. This is roughly the same as 1 over 100, right? Which is 0.01. A sub 3 is what? Oh, did I do that? See here, this is k equals 0, k equals 1, k equals 2, k equals 3 is over here, this one. What's 7 factorial? $5,040. So 1 over 5,040, right? And your book is, it's pretty lazy here. I like it. He's like, well, this is approximately, this is less than 1 over 5,000, right? Which, by the way, is equal to what? 0.2 times 1 over 1,000, right? Which is what? So there you go. Oh. Why did I say less than? Do I want less than? Do I want a less than there? I think I want that to be greater than, don't I? No?
Oh, okay, yeah.
Yeah,
You
yeah,
want
yeah.
L minus S sub n
Right.
plus an 8 and plus
Right.
1.
That should,
Unless it's the location.
right.
You want L minus, that would probably L minus S sub n to be less than n plus 1.
Right. I mean, more to the point, I want my a sub n plus 1, all right, to be less than the error that I'm looking for. All right? The error that I'm looking for is 0.0005 at most. So if a sub n plus 1 is 0.0002, it works. In other words, we can use what? We can use S, the second partial sum, to get the desired accuracy. So S2 is just 1 minus 1 over 3 factorial plus 1 over 5 factorial, which, by the way, is 1 minus 1/6 plus 1 over 120, which is what? This I don't know right off the top of my head. But your book says that that works out to, it only gives a fraction. It's 101 over 120. Thanks. Error. I'd like a decimal for that. Just a second, I got my calculator. I'm going to get it in a second here.
0.84.
What is that?
0.842. Yes.
0.842. What's the next digit?
Or 1/6.
0.81, 0.8416?
Yeah.
Okay. Yeah. So anyway, that says then the L is equal to 0.842, right? To 3 decimal places. And we can be sure of that by the alternating series estimation theorem. Oh, I am. Sorry for my switching less than to greater than. I mean, the opposite way around. That was silly. Any questions? So if you don't get lost in my silly arithmetic mistake and so forth, all I'm really saying here is if you want to approximate the sum of a series which is alternating, all you got to do is figure out what precision you want, and you just look for terms in the series to be the same size as that precision. And if you use the series summed up to that point, then you'll be within that precision. For example, we will soon learn that the sine of theta is equal to theta minus 1/6 theta cubed plus dot 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 dot, right? Well, you don't know that yet, but this is something we'll soon prove. And so if I say that the sine of, let's say, pi over 6 is just equal to pi over 6, all right, then I am within 1/6 times the pi over 6 cubed of the truth. See, because sine is an alternating series. If I plug in pi over 6, I get an alternating numerical series. And if I approximate sine theta by just theta, that has an error of at most the next term in the alternating series, which in this case would be that. Now you can check me on this. The sine of pi over 6 is what? That's the sine of 30 degrees. That's 0.5. It's 1/2. All right? What's pi over 6? What's 3.1415 blah, 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 divided by 6? You guys are making me get my calculator, aren't you? Then my calculator says back, pi over 6. Thanks for nothing. Okay, sometimes this calculator seems like a little smart alecky. Let's see here. 0.524, all right, to 3 decimal places. And what is pi cubed over 6 times 6 cubed? This is 0.024 approximately. Right. Ooh, I don't think I've kept enough decimals. 0.239. I don't think I kept enough decimals over here. This is a little bit fussy, isn't it? Let's see here. Pi divided by 6. That's 0.523. So as you can see, the sine of pi over 6 minus pi over 6 is what? 0.0235, well, 6. And that is what? That is less than 0.0239. But this one's pretty tight, right? But in fact, yes, the error in using pi over 6 for the sine of pi over 6 is less than the next term in that alternating series. Okay? This is very nice because sometimes you don't know how to actually sum an alternating series like this, right? Well, that's not true. I can tell you what this is. You know what this is? This is the sine of 1. Oh, do we end now? Oh man. Oh man. I was just